Good evening, ladies and gentlemen, and welcome to Lecture 3 of Topic 2 of Unit 4, Reflection. This video is going to be covering the main ideas of Chapter 16.4 of Book 1. Please complete this reading before class. Here is your learning intention and success criteria for this chapter. Please pause the video and attempt to complete the KS table down the bottom right corner. Okay, so looking here we can see that the intention is that you can explain the laws of reflection and use them to construct ray diagrams on flat mirrors. So we've got a skill verb there, construct ray diagrams to show location, and then calculate the angle. So there's a lot of skills on those success criteria there. In order to do this, we need to know what are the laws of reflection, and you probably need to know what a ray diagram is, otherwise it's a bit hard to do one. And then in terms of skills, can you construct one on a mirror? And can you calculate the angle of reflection? And likely in that skills I probably should calculate, can I construct it on a flat mirror, because curved mirrors are very different, but they are outside of our scope, so we don't have to worry about the complexity. Alright, so take a look at the room you're in. The walls, the keyboard, not the glowing part of the keys if you've got a glowing keys, but just the keys itself. The roof, frame of your monitor. The only reason you can see all these is due to reflection. Okay. Anything that does not emit light is only visible due to reflection of some light source. Now think about a mirror. You looked at yourself before. What do you see? Is the image the same as you? It is similar, but there is one big difference. If you raise your right hand, the image raises its left hand. To us, mirrors have what is called lateral inversion. Left becomes right, right becomes left, but up and down they are not touched. Now the other main thing that we notice, perhaps without always being aware of its significance in this sense, is that in a flat mirror our image is the same distance behind the mirror as we are in front of it. Okay? And what I mean by that is if my pen here is the mirror and I have, and I'm on this side of the mirror, my image will appear, try to get this right for you, about the same distance on the other side. Let's have a look at why. So there are two laws of reflection. Okay, we're going to look at light in terms of single rays. Objects do reflect light in all directions, otherwise you couldn't see it from all directions. We're just going to look at 2 or 3 rays coming off each point, and I'll show you what that looks like when we do our diagrams. When a ray hits a mirror, it will reflect. And now here's the first law. Both of these rays, including this middle one we call the normal, will be in the same plane. Okay, and this is the first law, and it's often overlooked. Like, I don't really think about it all that much, but what it means for us is that everything's just going to be drawn flat. Okay, so if we're dealing with a flat surface, the incident ray, the reflected ray, and a normal down the middle will all just be flat on the surface. The second law is the one that's important for us. Okay, the incident angle will be equal to the reflected angle. And do note that this comes from the normal, not from the surface. We'll see that in a diagram. And on a flat mirror, the complementary angle, so coming from the surface, they'll be equal. But for curved mirrors, this doesn't work. And Snell's law also, it won't work so when we do refraction. So just get used to measuring from the normal. Note, this formula is not written in the formula booklet. You're just expected to understand that this is an idea, this is a concept of reflection. Okay, so a ray diagram. Whenever we work with reflection or refraction, one really common skill is a ray diagram. A ray diagram is where we draw at least 2 lines from any given point. You only need 2 lines. Some texts like to use 3, but you only need 2. A minimum of 2 lines from any given point. They interact with the mirror, a prism, or a lens, and then we work out where the image is being made. So here's our first example. We have a woman here standing in front of a mirror, and we can see that the mirror is only coming about halfway up her body. Now I will get this out of the way and grab my ruler. So this stuff is actually kind of important that you are careful with your drawings, and you do try to make it as precise as possible. So I'm just going to draw somebody. They are 10 centimeters tall. Give them a head, really small head. Excuse me, sneeze. Let's give them some legs, really long legs, arms. I've never been a fantastic drawer. We all understand this. And we're going to draw a mirror some distance away from it. Let's find the halfway point first, because the mirror has them at the halfway point. 5 centimeters was there. And let's draw a distance. It doesn't matter how far away we go from them, but let's do 4 centimeters. It sounds like a good distance. 4 distance. This is what we're going to call our DO, which is symbols that will be useful for when we talk about refraction. For things that are a little bit outside of our scope, but they are useful to learn. So I'll teach you. Oops, didn't need all that. So we're just going to have a mirror, this bit here, that is half the size. And generally the symbols that we use for saying that something is reflective is just to put little dashes like this behind the surface. Alright. Now, your eyes are not at the top of your head. Even my bad drawings don't know that. So the eyes are here, right in the middle of the head. Let's figure out what this that's what I'm looking for, sorry. What this person actually sees, or what this head actually sees. Now, here we have this person's foot. Let's try actually draw it down to the floor. Here we have this person's foot, and this person's foot is 10 meters below, a little bit under 10 meters, I should say. 10 meters below the person's top of the head, or 9 and a bit meters below their eyes. And I'm curious, can they see? Can this person see their toes while looking in this mirror? And the answer is they can. Even though this mirror is only half their size, this person would see their whole height behind the mirror, through the mirror. Okay? And that's a fairly easy thing to prove. Okay? If it was, if the mirror wasn't half their height, they wouldn't be able to see it. But if you're buying a mirror for you to check yourself out, you want to look spiff and stuff, you only need half your body height in order to see your whole self. Mirrors that are full length, that go all the way down to the wall, well, they're great if you're a lot shorter and you need something that goes a bit further. But even someone who's only, say, yay high, only would need a mirror down to about here, and they would be able to see themselves in that mirror. So let's think about our laws of light. We know that light goes in a straight line. So I'm going to draw light coming off a straight line. I'm just going to draw it from the center of the person over here. The fact that the foot is drawn in front is because I can't draw. And I'm going to draw it at some straight line. That looks about good there. I'm looking for roughly just past the halfway point. Normally protractors would be good for this, and thinking about how far down. So there is some light that is leaving there, and it is coming from there back to the eye. Now, I'm not using a protractor. I really should. I'm not using one though. Remember the second law, that the incident angle equals the reflected angle. So this would be my angle of incidence, and this would be my angle of reflection. In this case, we're going to use R for reflection. I know we'll use R for refraction as well down the track, but you should be smart enough to differentiate between reflection and refraction and these sort of things. And if I had a protractor, I'd have to make sure these are actually correct, but we can see that they look pretty good. I think I've guessed pretty well there. I'd only be off by a little bit on either way, maybe a little bit back towards the midpoint there, but you can see that the angle here would equals the angles there. If this was higher, okay, there would be a larger incident angle, and so therefore it would go over there. If the angle is 45 degrees, okay, then you will end up with be able to see the object. If the angle is bigger than 45 degrees, so if it's 50 degrees, well then it'd come here and then it'd go off to there and you wouldn't be able to see down the bottom. So the whole reason for this is to do with isosceles triangles and geometry, which we don't need to worry about. We just need to be able to construct these diagrams. And so you can see all I did was I drew a line coming to the mirror and then I drew it back. I did have to make sure I got it to the right point though. So look at the distance, half it down the middle. If that's 9.8 centimeters, then I would draw a line to 4.9 centimeters down from the person. That way I've got the halfway point. But that doesn't tell us where we see the image. And what I'm going to do here is backtrace the ray that went to the eye, because when we look through a mirror, we don't like see it bouncing. We see that there is something on the other side. Now, I'm just going to set this up a little bit. This is about 4 centimeters. I measured this out as 4 centimeters over here. So if I line this up at 12, so it's going to go to 16 for 4. And 16. You can see that our ray looks like it's going to come pretty close to 16. A little bit past, because as I said, my drawing's not that great and I should have used a protractor. So if I'd done this perfectly, that should have come out if this is from 4 centimeters from this point to the line perpendicular to the mirror, this will be 4 centimeters as well. Okay, so this is still DO, and this is what we will call DI. And realistically, DO, or in a real sense, this is what does happen, but Mr. Warren can't draw, DO will equal DI. Okay. So there's one ray, but where's the top of the person? Well, we're going to do the same thing. This time, though, I don't need to draw a very shallow ray. I'm going to put just a couple of lines along it to say from the eye to the head. Okay. And so halfway between that and that looks to be about there. And so now there's the ray out. And there's the ray coming from the top of the head. And again, we're just going to backtrace the ray that goes back to the eye. Which will be the 11. About 14.5. Should be at 15, but pretty close. Might should be a bit closer than I thought. And so that would be the top of the person's head. And I have a feeling that some of my straight lines were not parallel with each other. And so then we would know, oh, well, the person would be there. That would be the top of their head. Then they got arms, there-ish. Then they got legs, there-ish. Okay, and so that the distance to the object is equal now to the distance to the image. Let me bring back the example picture with a much better picture than what I drew. And now, here, significantly better, you can see that the angle here and here will be the same, incident equals reflection, and so this light ray that's come up is intersected with the mirror and bounced back to the person's eye, and so the person sees the image being created on the far side, top of the head to the mirror and back. So you don't need a full-length mirror in order to see a full-length image, so don't waste your money. Let's have a look at another example. Nice straightforward one in this case. We have a chess piece, we have an eyeball. Where would you see the chess piece? Okay, let's do exactly the same thing. Let's see if I can make a slightly more accurate drawing this time. Now, the fact that the mirror in this case is bigger than the piece in the eye doesn't matter. It's just that they've drawn it straight in without having to overthink it too much. That looks pretty perpendicular to me. And we're going to draw a chess piece, but my chess piece is just going to be a bad rectangle. And this is my eye up here. Single point. I don't want it to be anything particularly amazing. I just want it to be a straightforward single point. I'm going to take this one a little bit more carefully this time to show you what to do. Okay, that is 7.5 centimeters, and half of 7.5 will be 3.75. So there's 3.5, 6, 7. So that about there is the middle point between them. The reason I want the middle point is so I know where on here my ray should go to come from the top. When I go from the bottom, I'm going to need another ray. I'll just turn this around a little bit so I can look a bit better. Ray goes to there. Ray goes to there. And now I'm going to back trace this over here. There we go. There we go. Okay, so that's going over there somewhere. Let's have a look now from the bottom. Let's do, well, the bottom we know will end up over here. Let's draw another point. Let's also make this point part of the eye, because we want to know exactly where that's going to go to, so we need to do some sort of convergence here. Now, let's go from there to there. Sorry, my head's getting in the way. That is 7.2, so that's going to be 3.6. That's not too bad, so now we can go make sure that lines up properly there, nice and parallel. So that looks to be about there-ish. And now this time I'm going to draw the same line, just we can see that it'll be a little bit at a slightly different angle. And now we can back trace it over here. And we see that, okay, that's about where it crosses over. Yeah, unfortunately, not my drawings are that great. And so we see here that, well, where it's converged, it's obviously a little bit bigger, so my drawing is not amazing. But the goal is to say, okay, well, if I have two lines hitting some receiver over there, then you will end up having an image being constructed. Okay? That's how we're meant to draw it. Now, mirrors, you know, I really doubt mirrors would be really a question that you'd be asked. Lenses, sure. Mirrors, probably not so much. But let's have a look at what this should look like. So we can see here we have our two rays coming off. I probably should have picked a point that's a bit further away up here just to make it a bit easier to do my drawings. And we see here's the bounced off, and they've back traced the line to find where the convergence is. Their drawings are a lot better than mine. Okay, you saw how to do it, but obviously my accuracy is not all that fantastic. So, there's a bit of terminology here. And that is whether the image is virtual or real. So images are always classed as whether they are virtual or real. Now, with mirrors, like the flat mirror that you see, curved mirror, any image that appears behind the mirror is what we call a virtual image. It's not really there. You can't touch it, you can't use it to show, to put onto another surface. It's just something you see through the mirror. Okay? You can get real images with holograms, and they normally involve concave mirrors, but as I said earlier, that's outside the scope of the unit. Now, in comparison, when we look at lenses, we're going to see some real images, which are images that are being put onto another surface. Your glasses, if you wear glasses or someone in your family wears glasses, they're a really good example of a real image. The projector at the movie theatre, how long has it been since we've been to a movie theatre? They are creating a real image on the screen that then is visible for everybody else. So, in this video, we've gone through the following the laws of reflection and how to draw ray diagrams on flat mirrors. Okay, so for your entrance slip to class, please complete questions 1 to 7 in chapter 16.4 Check Your Learning PDFs, and copy your answers into the 4.2.3 space on eLearn. Remember, this is book 1. Thanks very much for listening, guys. Have a great evening.